Okay, guys, welcome. Today we're going to talk about some quadratic and other types of inequalities. Now that we've looked at many of the different methods that we can use to solve quadratic equations and look at graphs of quadratic functions, we can now talk about an extension of this, which will allow us to look at quadratic and some other types of inequalities. Now, when we say a quadratic inequality, we just mean a quadratic equation more or less, but if instead of an equal sign, we've replaced the equal sign with one of these four inequality signs. And of course, here there are some examples, right? The sort of the key feature is that you have a quadratic function, and instead of an equal sign separating it from the zero, you have a inequality sign. Now, what we're essentially looking for is, of course, the solution to a quadratic inequality, and that is just going to be the set of all values that make an inequality the true statement, right? So what we need to do is, now, in most cases, this set of values will be an infinite collection or an infinite amount of values. So what we need to do is to be able to be comfortable in expressing our answers in interval notation as well. Or equivalently, we can also do on a number line as well. Now, what I want to sort of stress here before we get to this step-by-step process is that you essentially are going to have three scenarios. And I guess one thing that we can say is the first step in solving these is you're essentially going to treat this as an equation first. And what you get for your solutions are the boundary values. Now, in order to extend this idea from what we currently know, we know that when there are no solutions to a quadratic function, we either have something that's always positive or something that's always negative, right? So if your A term is positive, and which indicates that your graph is going to open upwards and you can't find any x-intercepts or you can't find any solutions, you're going to get a graph that is never going to touch the x-axis. So it's either going to be always positive, and of course, so this is the a greater than 0 case, or it's going to be always negative, and that's if your a term is less than 0. So no solutions is one possibility. If you get one solution, then that means that your parabola is only going to intersect the x-axis at a single point, and it's either going to look like the top one. Of course, this is again the a greater than 0 case, and this bottom one is the a less than 0 case. And of course there it's going to be almost entirely positive or almost entirely negative, except for the single point, of course, for which it's 0 when it crosses the x-axis. Now the interesting case comes into play when there are two solutions, because then your graph looks something like this. Now in the top one, you sort of have these two sections here where the graph is positive, and then you have this other section down here, of course, where the graph is negative. So depending on your original inequality, we're interested in either the two yellow sections or the single green section. So, and of course, as you could look at the same sort of scenario for the one below, the a negative case, of course. And again, you're either interested, depending on the original inequality, you're either interested in the single positive part this time or the two negative parts. So this sort of demonstrates the importance of first treating that inequality as an equation and then finding the solutions if they exist, and those would give you the boundary values. Now, essentially, once you have those boundary values, you're then looking at a number line, and your boundary values will either be closed or open circles depending on your inequality sign. So if you don't include the equal sign, we would use an open circle. And if you do include the equal sign on your inequality sign, those would be indicated by a closed circle. Now, later on, we'll talk about what are called rational inequalities, which essentially just means that you're looking at a rational equation except with an inequality sign. And you would also want to point out any values that make the denominator 0. And they would also be boundary values, but of course we can't have our denominator equals 0, so those automatically would get an open circle. So we'll do 1 or 2 of those later. Now at this point, you sort of have separated your number line into different sections based on what your boundary values are. So what you need to do is figure out what's going on in between each of those boundary points. So the simple way to do that is to select a test value within each section and then determine if you get something that's positive or something that's negative. And from there, you can determine whether or not that would satisfy your original equality. And then of course, 5 and 6 are just sort of putting a bow on the end of the problem, just presenting your answer in the form of what you want, which in most cases is just interval notation. Interval notation. Okay, so without further ado, let's go ahead and do one. So of course, so in this case, we want to solve x squared minus 2x minus 8 greater than 0. So the first thing that we want to do is we treat this as an equation and we get our boundary values there. So if we just were to solve x squared minus 2x minus 8 equal to 0 to get the boundary points, so this will give the boundary points. Well, we know that we can factor this, hopefully. And of course, in this case, we can. So we need two numbers that multiply to -8 and add to a -2. So it looks like -4 and +2 will do the trick. So of course, this first one would give us x is equal to 4. And the second one would give us x is equal to -2. So these would give the boundary points. So these are the boundary points. Okay, so that's step 1. Now step 2 is to draw a number line, and we'll indicate our boundary points here. So somewhere down here we have -2, somewhere up here we have 4. And now if we look at our original inequality, our inequality sign does not have the equal sign. So we want to use open circles here. So on 4, we have an open circle, and on -2, we have an open circle because that's what the original inequality would need for a satisfactory answer. Okay, now our third step, I think I'm keeping the steps all lined up here. Oh, so third step is rational inequality. So in this case, we don't need the third step because we have just a simple quadratic inequality. So now the fourth step is to pick a test value in each section of our number line. So for example, I could test -3, since that's less than -2. In this center region, I could test 0. And in the upper region, we can use 5. Now, I recommend use your test values in the factored version of your original inequality. It'll make finding the answers a little bit quicker because we're not concerned with what the actual answer is. We're concerned if we have positive or negative. So this will help find positive or negative quicker. And I'll show you what I mean by that. So for example, if I want to test x equal -3, well, my factored version is x minus 4 times x plus 2. And of course, we want this to be greater than 0. So if I plug in -3 here, I'll get a -7. If I plug in a -3 into the second part, we'll get a -3 plus 2, so a -1. Now, of course, -7 times -1 is +7, but more importantly, that's positive. So since this part is positive, we will ultimately include that in our final answer. Now, of course, we can do a similar thing for 0. And if we plug in 0, we get a -4 times a +2, which is -8, which is less than 0. So we will ultimately not include that in our final answer. And last but not least, we can test x is equal to 5, right? And then we get a 1 times a 7, which is +7, which is, of course, positive. So we will include that. So again, so now we just need to wrap this up by stating what our answer will look like. So again, we want where this is positive, so where is this positive? Well, it's positive from -infinity to our first boundary point, which is -2, and we don't include that since we have an open circle. And then we're going to join that, we're going to union that with everything from 4 to +infinity. So that's our solution for this first inequality. Okay, let's try another one. Now in example 2, we need to move everything to one side. So the first thing I'm going to do is I'm going to move 25 to this side. So then I have x squared minus 10x plus 25 greater than or equal to 0. So of course, first thing I want to do is treat this as an equation to get my boundary points. So if we factor this, we get an x, let's see, it looks like an x minus 5, x minus 5. And of course, if you recognize the special form there, you could see that this is a perfect square. So we get x minus 5 squared is equal to 0, which just gives one answer of x equals 5. So that's our single boundary point. So on the number line, we actually only get 1 point here. We just get 5. And now since we have the equal sign this time, we need a closed circle. So we'll put a closed circle of 5. Now again, step 3 doesn't apply here because we have a non-rational inequality, so we can go right to step 4, which is to look at some test values. So for example, we could test, so let me put this in green. So we could test, for example, 0 and 6. And again, if we do this in the factored version, that will make life a little bit easier for us. So the factored version was x minus 5 squared greater than 0. Excuse me. And one thing that's nice about this is that this will always be positive because you're squaring something. But if you don't believe me, let's look at it. So if we test x equals 0, well, we're going to get -5 squared, which is positive 25, which is positive. So that section is positive. If we test x is equal to 6, we get 6 minus 5, which is 1 squared, which is 1, which is also positive. So both sections are positive. And of course, since we include 5 in this process, your answer, your solution, again, we want this to be positive. So the solution is everything. It's -infinity to +infinity, or you could say all real numbers. All right, so either one of those would work in this case. So that's an example where the one solution would actually produce the entirety of the real numbers for your solution. Okay, let's look at one more that's a little bit more tricky, but nothing that we can't handle. Now, again, first thing we'll do is we'll look at this as an equation to get our boundary points. So first thing that you would notice about this, or that you would hopefully notice about this, is that we can factor out a 4x, and we would get an x squared plus a 2x, and then minus a 3. And now this quadratic part here, we could factor further, as we need two numbers that multiply to -3 but add to a +2, so we would need x plus 3, x minus 1. So our fully factored version of this is 4x times x plus 3 times x minus 1. So we get x is equal to 0, we get x equals -3, and we get x is equal to 1. So we actually get 3 boundary points here. So that will come into play in this next step here. So now we have a boundary of -3, we have boundary value of 0, and we have a boundary value of 1. And again, we have the equal sign here, so that's going to tell us that each of these are going to get a closed circle. Okay, so the next thing we need to do, again, we're not looking at a rational inequality, so we just need some test values here. So for example, we could do -4, we could do a -1, we could do a 1/2. Unfortunately, we can't avoid a fraction there. And then in this part, we could do a 2. And of course, we can use the factored version. And these are with the test values. Okay, so we want to look at 4x times x plus 3 times x minus 1. And we want to do that, for example, for x equal -4 first. Now, if we plug in a -4, 4 times -4, I'm just going to write whether it's positive or negative, since that's really all we care about. So the 4x will be negative. X plus 3 will also be negative, because that's -4 plus 3 is a -1. And then -4 minus 1 is also negative. So if you multiply 3 negatives together, you get a negative. So that's going to be this section here will be negative. All right, moving on to x equals -1. If we plug in -1, 4x will still be negative. But now -1 plus 3 will be positive, and -1 minus 1 will still be negative, and 2 negatives and a positive will give a positive. So this section will be positive. Now if we plug in a 1/2, four times x is now positive. 1/2 plus 3 is positive, but 1/2 minus 1 will be a -1/2, which more importantly is negative, so that will be negative. And last but not least, if we plug in 2, we're going to get a positive. 4 times 2 is 8, which is positive, and then we get 2 plus 3, which is positive, and 2 minus 1 will also be positive. So 3 positives multiplied together will also give positive. Now in this particular inequality, we want where this is negative, right? We want this to be less than 0, so we want it to be negative. So we actually want the red sections here, the 2 negative red sections here, right? So then our solution is -infinity to -3. And since we have closed circle, this will get a bracket, and then we will union this with 0 to 1. And again, both are included, so they will both get brackets. And there's our solution for that one. Okay, so hopefully those are not too bad. Now I want to do two examples of how this looks like for a rational inequality, and then we will talk, and then we will, of course, wrap this video up. Okay, so how is this different for a rational inequality here? So again, the first step is no different. We want to solve this if this were equal. And of course, I would actually need to bring this 3 over, right? I guess if we want to be thorough here, we should say this is x minus 4 over x plus 2 minus 3 greater than or equal to 0. And we'll work more with that later, but for now, let's just solve for our boundary points here. So in this case, if I want to, and actually this should be an equal sign. So if we solve this, I would move the 3 back over. And then if I think of my 3 as 3 over 1, we can then cross multiply, and then we get x minus 4 is equal to a 3 times x plus 2. So then we get x minus 4 is 3x plus 6. And if we move some stuff around, if we move this x over and subtract this 6 over, we will get that 2x is equal to negative 10. So we get x is equal to negative 5. Right? Now, in this case, I also need to be careful, and I need to also include x equal negative 2. And of course, why do I include that? Because that would make the denominator 0. So those are my boundary points. Now, my number line will now look like this. So two boundary values of negative 2 and negative 5. Now, negative 5, we're going to give a closed circle for because of our inequality sign containing the equal sign, but negative 2 makes the denominator 0. So we don't have a choice. That has to be an open circle. Okay. Now, in this final step, there's sort of two ways that you can handle this. Now, if you wanted to, you could take this inequality here, and you could find a common denominator for the 3 so that you have one single rational function. Since this is not too difficult to calculate, we're just going to go ahead and we're going to calculate it and see whether or not we get positive or negative numbers. So for example, we still need to pick some test values. So this was actually step 3 right here. Step 4 would again be to pick some test values. So we could use, for example, negative 3. We could use wait a minute, my number line's all jacked up, right? So I actually need to switch these two. This should be negative 5, and this should be negative 2. All right, let's start this over. Okay, and let's pretend I know what I'm talking about. So now, for this number line, negative 5 is less than negative 2, so I need this. Now, negative 2 we don't include because it makes the denominator 0. Negative 5 we do include because of the inequalities. Okay, we're back on track. So for my test values, we could use something like negative 6, negative 3, and then we could use 0. That's a little better. Okay, so let's see what happens. So if we plug in x is negative 6, we're going to get a negative 6 minus 4, which is a negative 10, over a negative 6 plus 2, which is a negative 4, and then we want to subtract 3. So this is a 5 over 2 minus 3. And since 5 over 2 is about 2.5, well, it is 2.5, this will be less than 0. So in this section, we have negative. Okay, if we plug in -3, well, we're going to get -7 over a -1, right? -3 minus 4 is a -7. -3 plus 2 is a -1. And then subtract 3. But of course, this is just 7 minus 3, which is positive. So this section will be positive. And finally, if we plug in 0, we're going to get a -4 over 2 minus 3, which is -2 minus 3, which of course is negative. So now what do we want as our final answer? Well, we want this to be positive, or we want it to be greater than 0. So in this case, our solution is where this is positive. So from -5 and include it, so a bracket, to -2, but don't include it, so a parenthesis. So there's our solution for this one. Okay, we'll do one last example for this video, and that will conclude this lesson on solving different types of inequalities. Okay, so again, first things first, let's find our boundaries. Boundary points. So we need to solve, well, when is this thing equal to 0? And of course, when is a fraction equal to 0? Well, it's when its numerator is equal to 0, or if you like, you can simply cross multiply this thing. Either way you think of it, you're going to get that x minus 2 times x plus 5 is equal to 0, which gives you x is equal to 2 and x is equal to -5. And of course, we have a rational inequality here. I know this is like step 3, but I'm too excited. We're going to do it now. So since we have a rational inequality, we also need to include when x is -3, since that, again, that makes the denominator 0. So we also need to include that one. Okay, so last but not least, we also need to do a number line here. So what are 3 boundary points? Let's see if I can do it right this time. We have -5, and then -3, and then +2. Now we also have the equal sign here, so we're going to get closed circles on our solution points. So our solution points were 2 and -5, so I need to put closed circles on them. And then since -3 makes the denominator 0, we're going to include that with an open circle. All right. So now for some test values, we could use, for example, -6. We could use -4. And we could use 0. And we could use 3. So now if we plug these into our function here, so if we look at x equal -6, so we're going to get, so -6 minus 2 would be a -8, but more importantly, negative. -6 plus 5 is also negative. And if I have a -6 plus 3 in the bottom, that will also be negative. So what this will end up being is a positive over a negative, which is negative. So that's that first section. If we test x equal -4, we'll get a negative, we'll get a positive this time, and then this will still be negative. So what will happen is we'll get negative over negative, which is positive. So that section is positive. If we plug in 0, we get a negative times a positive over a positive. So we get negative over a positive, which is negative. So this section is negative. And finally, if we test x equals 3, we get a positive, positive, and positive again. So everything is positive, and overall the whole thing is positive. Okay, so we have everything marked off, so we can now say what our solution is. So our solution is where this thing is positive, right? If we look at this inequality sign, we want it to be positive. So it looks like we want -5, and of course include it because we have a closed circle, to -3, but don't include that because we have a closed circle, open circle, sorry. And then of course we will union that with a 2, which we are including all the way out to infinity. So there's our solution for that one. Okay, so that's going to conclude this video. Hope you guys enjoyed it, and I will see you next time.